In this lecture, we will be talking about assessing causality and the process of causal inference in epidemiologic research. So, epidemiologic research is the subject of a lot of criticism sometimes, and this criticism has to do with the fact that there are many conflicting studies in the literature, and observational studies, which are the backbone of epidemiologic research, are not considered to be as methodologically rigorous as experimental study designs. Now, properly conducted experimental designs allow one to demonstrate that a particular factor actually causes a particular outcome. However, it is not as cut and dry in observational research. Therefore, epidemiologists must use other methods for inferring causal relationships. Now, Gersman defines causal inference as the process of deriving cause and effect conclusions by reasoning from knowledge and factual evidence. So what exactly is a cause? In epidemiology, a cause can be considered an event, condition, or characteristic without which the disease would not have occurred. The Henle-Cope postulates are adequate rules when we're attempting to determine a single causal factor. However, in many communicable and most non-communicable diseases, a single cause does not contribute to disease development. Many diseases are, in fact, multifactorial, requiring the presence of several risk factors for the development of disease. A sufficient cause means that the exposure alone will produce the disease. A necessary cause means that the exposure must be present for the outcome to develop. Now, a cause may be necessary but not sufficient to produce a particular outcome. It may be sufficient to produce an outcome on its own, but not necessary. Or a cause might be both sufficient and necessary. Now, frequently, one exposure or risk factor alone is not enough to produce the disease. So for many diseases, especially for most non-communicable diseases, many factors must be present for this disease to develop. Now here we see just kind of a breakdown of the possibilities of a multifactorial cause of disease. So we have A, B, C, D, E, F, and G. All of these are component causes of disease, or as we like to call them in epidemiology, risk factors. Now A is the only necessary cause. If A is not present, disease X will not manifest. Now note that A is necessary, it's not sufficient. A must be present, but it must be present in conjunction with these other factors. However, none of the other factors are considered necessary because as long as there's several of those other factors plus factor A, then the disease will develop. So A is not sufficient to cause disease in this example. So there's 4 types of causal relations. The first is that a factor is both necessary and sufficient, meaning that the disease will only occur if the factor is present and the exposure will always lead to disease. This type of relationship is rarely encountered. A factor may be necessary but not sufficient, and that the factor must be present for the disease to manifest, but the factor alone will not produce the disease. No, so that's the example we had of factor A in the previous slide. A factor may be sufficient but not necessary, meaning that the factor alone can cause the disease process, but other factors by themselves or in conjunction can cause the same disease. So, for example, vitamin B12 deficiency can cause anemia. It is a sufficient cause of anemia. However, there are other things that can cause anemia as well, so vitamin B12 deficiency is not necessary to cause anemia. Now, finally, a factor may be neither necessary nor sufficient, meaning that the specific factor can combine with other factors to produce disease. However, the disease may be produced even in the absence of this factor. Now, this is the most common causal model that's observed in chronic diseases. So the completion of a sufficient cause is synonymous with disease occurrence, though it might not necessarily lead to disease diagnosis. Component causes can act far apart in time. They do not have to occur simultaneously or even temporally close together. A component cause can involve the presence of a causative exposure or the lack of a preventive exposure. Finally, blocking the action of any component cause prevents the completion of the sufficient cause and therefore prevents the disease by that pathway. There are, generally speaking, 4 types of factors that play a part in the causation of disease. Predisposing factors are those factors that make a person more susceptible to the disease. These can include things like age, sex, genetic traits, or even prior illness. Enabling factors are external factors that may contribute to the development of disease. Examples include low income, poor nutrition, unsafe housing, and other social and economic factors. Precipitating factors are those factors that are associated with the onset of disease, for example, exposure to a specific pathogen or harmful substance. Finally, reinforcing factors are those factors that may aggravate an established disease, such as repeated exposure or poor environmental conditions. All of these types of factors can be termed a risk factor. A risk factor is any factor that is positively associated with the development of a disease. Now, Hill's criteria of causal inference, which we also will hear referred to as Bradford-Hill's criteria of causal inference. And the purpose of Hill's guidelines is to help determine if associations are causal. They should not be used as rigid criteria to follow without question. They are not intended to be hard and fast rules. Rather, they are intended to provide a framework of reference for building support for a causal association. So then the temporal nature of an exposure-disease relationship is one of the most basic and most important of the causal criteria. Simply put, the exposure must precede the development of the disease in time. Additionally, there must be sufficient induction or latent period between the exposure and the effect. For example, if someone begins smoking 2 months before they develop lung cancer, we may not want to use smoking as a contributing cause of the development of lung cancer. Now, temporality is the only one of Hill's criteria that everyone seems to agree on, and it's the only one of Hill's criteria that absolutely has to be met in order to establish a causal relationship. Now, prospective studies do a good job of establishing the correct temporal relationship between an exposure and a disease. Now, the stronger the association between an exposure and an outcome, the more likely it is to be causal. Weak associations are more likely to be influenced by confounding or bias. Now, it's important to note that just because a relationship is weak does not mean that the relationship is not causal. It's just harder to rule out bias and confounding. Now, a dose-response relationship, which is also sometimes referred to as a biological gradient, occurs when changes in the level of a possible cause are associated with changes in the incidence of the effect. So persons with increasingly higher exposure levels should have increasingly higher risks of disease. Now, there are instances where some exposures might not have a dose-response effect, but rather a threshold effect. So below the threshold, there's no adverse events, and then once you reach the threshold, and then your risk increases. That being said, a clear-cut dose-response relationship demonstrates strong causal evidence. Consistency simply means that you come to the same conclusion based on the results of different studies. So when you find the same results in various study designs, you can be even more confident in your causal conclusions, as each type of study design minimizes different types of bias. Therefore, you're more confident that you're demonstrating a true relationship and the results you're seeing aren't due to bias or confounding. So replicating the association in different samples with different study designs and different investigators gives stronger evidence of causation. Now, it's important to note that there are sometimes good reasons why study results differ. For example, one study may have looked at low-level exposures, while another looked at high-level exposures. An association is biologically plausible when it is consistent with other knowledge, meaning that a biological or social model exists to explain the association, and that the association does not conflict with current knowledge of natural history and the biology of disease. Now again, just because it doesn't fit with a currently known biological model doesn't mean it's not necessarily a causative factor. The biological model could be wrong. But if you can pose a biological reason for why you're seeing this exposure-outcome relationship, you have stronger evidence of causality. Now, analogy refers to if the relationship is similar to other observed exposure-disease relationships. Specificity is that a single exposure should cause a single disease. Now, specificity is really a holdover from the concepts of causation that were developed for the infectious diseases, those Henle-Koch postulates that we were talking about earlier. There are many exceptions to this guideline. For example, smoking is associated with lung cancer, as well as many other diseases like oral cancer, heart disease, and so on. Additionally, lung cancer can result from smoking, but it can also result from other exposures. So we know smoking is actually a strong causative agent in the development of lung cancer, but it doesn't necessarily meet the specificity criteria. So this is an example of how the Bradford-Hill criteria, the more you can put them together and the more of the criteria that you meet, the more confident you are of a causal relationship, but not meeting a particular criteria does not mean that the relationship is not causal. Now, the best evidence for causation comes from randomized controlled trials. However, it's relatively uncommon to have this type of information. Cohort studies follow randomized controlled trials as the next best study design, especially when we're talking about observational research, since they can minimize bias when well conducted, and they allow for establishing the temporal relationship between cause and effect. Case control studies follow cohort studies as the next best design, but in case control studies you have a greater risk of bias than in cohort studies. Cross-sectional studies do not allow for establishing the time sequence of events, and ecological studies provide the weakest evidence, since there's always the danger of the ecological fallacy, incorrectly extrapolating population level data to the individual level. So the Bradford-Hill criteria are a framework from which to study associations before concluding a causal relationship exists. None of the criteria alone indicates a causal association, and only temporality is an absolute necessity for concluding a causal association exists. Now, Nurs defines bias as a systematic error in the design, implementation, or analysis of a study that results in an estimate that differs from the truth. Bias can create a spurious association when there really is no association. It can mask an association when one really exists, and bias is primarily introduced by the investigator or study participants. Bias does not mean that the investigator is prejudiced. It can arise in all study types and occurs in the design and conduct of the study. It can be evaluated, but not fixed in the analysis phase. Now, random error does not bias measures. Random error refers to all the extra variation not due to the true ability, but with no consistent pattern. Random error does not bias measures because there is no rhyme or reason to the variation. It's really just noise in your data. Now, systematic error occurs when the information we collect consistently reflects a false picture of the concept we seek to measure, either because of the way we collect the data or the dynamics of those who are providing the data. Selection bias can occur whenever an investigator selects his source population or determines eligibility criteria, or whenever conditions influence the subject's choice to participate. In other words, results from procedures used to select subjects into a study lead to a result different from what would have been obtained if the entire population targeted had participated. Selection bias is most likely to occur in case control or retrospective cohort studies because the exposure and outcome have occurred at the time of the study selection. Selection bias can also occur in prospective cohort and experimental studies from differential loss to follow-up, because this impacts which subjects are available for analysis. Exclusion bias is a type of selection bias in which the investigators apply different eligibility criteria for the cases and controls, or for the exposed and not unexposed in a cohort study. For example, if you're conducting a study of drug abuse cases in the emergency room, and then you choose to find your controls using a phone interview of individuals whose addresses are within the same neighborhood, your control population ends up excluding all people without a phone, or people who are homeless, who we know are more likely to end up in an emergency room. Bergson's bias is a mathematic phenomenon that appears when studies use hospital admission rates. Hospitalization rates for individuals with the target disease will differ from the rates of those with the control condition. Selection bias in a case-control study occurs when controls or cases are more or less likely to be included in the study if they have been exposed, so inclusion in the study is not independent of exposure status. When selection bias happens in a case-control study, the relationship between the exposure and disease observed among study participants is different from the relationship between exposure and disease in individuals who would have been eligible but were not included. The odds ratio from a study that suffers from selection bias will incorrectly represent the relationship between exposure and disease and the overall study population. So let's walk through an example of selection bias in a case-control study. We'll start with the research question, do pap smears prevent cervical cancer? The cases for this study were diagnosed at a city hospital. Controls were randomly sampled from hospitals in the same city by canvassing the neighborhood on foot. The table on this slide indicates the true relationship that people with cervical cancer were 54% less likely to have pap smears than those without cervical cancer. Now let's recall that cases come from the hospital and controls come from the neighborhood around the hospital. Now for the bias. Only controls who were at home at the time the researchers came around to recruit for the study were actually included in the study. Women at home were less likely to work and less likely to have regular checkups and pap smears. Therefore, being included in the study as a control is not independent of the exposure. The resulting data are what you see in the table. This data indicates there is no association between pap smears and risk of cervical cancer. So women who were at home during the day were not representative of the whole study population that produced the cases. They did not accurately represent the distribution of exposure in the study population that produced the cases, and so they gave a biased estimate of this association. Selection bias in a cohort study occurs when selection of the exposed and unexposed subjects is not independent of the outcome. This can bias the risk ratio. So let's walk through an example in a cohort study. Now, researchers conducted a retrospective study of an occupational exposure and disease in a factory setting. The exposed and unexposed groups were enrolled on the basis of prior employment records. The records are old and many were lost, so the complete cohort working in the plant is not available for the study. If people who did not develop the disease and were exposed were more likely to have their records lost, then there would be an overestimate of the association between exposure and disease. This table shows the true relationship between exposure and disease. The disease is not associated with the exposure. Now let's say that 200 records were lost, all among the exposed who did not get the disease. If we lose 200 records among the exposed who did not develop the disease, we end up with a risk ratio of 1.25. We see a relationship that isn't truly there. So what can we do about selection bias? Once the bias has occurred, there is little or nothing we can do to fix it. We must avoid selection bias in the design and conduct of the study. For example, by using the same criteria for selecting cases and controls, obtaining all relevant subject records, high participation rates, and taking into account diagnostic and referral patterns of disease. Information bias occurs when there is some flawed component in measuring exposure or outcome status, leading to inaccurate information. In other words, an error that arises from systematic differences in the way information on exposure or disease is obtained from the different study groups. Information bias occurs after the subjects have entered the study. There are four main types of information bias: recall bias, reporting bias, surveillance bias, and misclassification bias. Recall bias occurs when people with the disease remember or report exposures differently, either more or less accurately than those without the disease. This can result in an over or an underestimation of the association. Some solutions to combating recall bias include using controls who are also sick but with an unrelated illness, using standardized questionnaires that obtain complete information, and masking subjects to the study hypothesis. In this example, the cases are underreporting the exposure. You can see that the true association is that cases are almost 3 times more likely to have the exposure. However, with the recall bias, the association appears much smaller. Interviewer bias occurs from the systematic difference in soliciting, recording, or interpreting information. It can occur whenever exposure information is sought, when the outcome is known, as in a case control study, or when the outcome information is sought when exposure is known, as in a cohort study. So what are the solutions? You can mask interviewers to the study hypothesis and disease or exposure status of the subjects. The use of standardized questionnaires or standardized methods of ascertaining the outcome or exposure can also help decrease interviewer bias. Misclassification occurs when the subject's exposure or disease status is erroneously classified. So misclassification occurs when you call someone a case when they actually do not have the disease, or you call someone a control when they actually do have the disease, or you classify someone as exposed to the risk factor when they were truly unexposed, and so on. Misclassification can be differential or non-differential, which we will discuss in just a moment. To deal with misclassification, you can use multiple measurements or different types of measures to ensure that you are correctly classifying your subjects. Now, as I said earlier, misclassification may be non-differential or differential. In non-differential misclassification, the misclassification is random throughout all study groups. In non-differential misclassification, the bias is introduced in a random fashion and equally affects all study groups. This may balance out between the groups, diminishing the overall bias in the resulting association. This type of random misclassification increases the similarity of the study groups and will bias the relative risk for any true exposure disease association towards the null. Now, differential misclassification occurs when the misclassification is non-random. In differential misclassification, the rate of misclassification is higher in either the cases or controls, or the exposed or unexposed group, introducing the potential for serious error. Depending on which group is more likely to be misclassified, the true exposure-disease relationship may be overestimated or underestimated. Now, most epidemiologic studies measure disease frequency in 2 or more groups that differ only on the exposure of interest. The 2 measures of disease frequency are combined into a single measure of association, so the risk ratio, the rate ratio, or the odds ratio, among others. The next step is to evaluate whether the result that has been observed in the data is true, or whether the observed result is false, and there is an alternate explanation. This is the process of assessing the validity of a study result. There are 3 alternate explanations. Random error or chance was responsible for the study finding. Bias, a systematic error in design or conduct of the study, which leads to error in estimation of the association. Or confounding, a third variable that is distorting the association. Only after deciding that an observed association is valid is it proper to form an opinion on whether the exposure causes the disease or whether the results are generalizable to a larger population. A couple of quick notes about samples and populations since we haven't really discussed this much yet. We typically cannot study a whole population due to many issues, time, money, logistics, and so instead we choose a sample from the population. Based on the sample, we make an inference about the larger population. It's very important in trying to make predictions about a population that the sample you take from the population is random. If you take a sample that is not randomly selected, for example, if I were conducting a survey of SLU students and I decided I could just survey my classes because it was convenient, my statistical model would probably not give me good information about the SLU population as a whole. Now, why is this? Because this is a class comprised of all graduate students, almost all of whom are nurses, and this sample is not the same as the SLU population. In statistics, we say that this sample is not representative of the population we're interested in. Simple random samples are unbiased. Each unit has the same chance of being chosen. They're also independent, so the selection of one unit has no influence on the selection of other units. There are several ways to get a random sample, and all are variations on simple random sampling. A simple random sample can be taken in a number of ways. You could write down or get a list of the entire population and then use a random number generator to select a sample at random. This is often done in phone surveys. You could put the names of everyone in the population on pieces of paper and draw them from a hat. But instead, many studies use variation on the simple random sample that takes advantage of information you may already have about the sample. So for a stratified sample, you divide your population into categories and take a simple random sample from each category. For example, at SLU, instead of a simple random sample of the whole student body, we could take a sample from each major, or from each year, or from each campus. A cluster sample is where you group the population into small clusters and take a simple random sample of the clusters and talk with everyone in each cluster. For example, if you were interested in studying the population of St. Louis, you might divide the city up into census blocks and then take a simple random sample of census blocks and then talk to everyone in each block you chose. Finally, a systematic random sample starts with a random individual in the population and then selects every nth person after that. For example, you might pick someone at random in line at the movies to interview and then ask every 10th person after that to interview as well. Most statistical methods depend on the sample being random, so that it is a good representation of the population, so that characteristics are distributed through the sample in the same way as they are in the population. Now, there are other ways to sample that are commonly used, but often don't give results that are quite as dependable. Now, inferential statistics are the method from which we can assess the true relationship between an exposure and disease based on data from a sample. The actual study results will vary depending on who is in the sample, and this is known as sampling variability. Now, the goal of hypothesis testing is to estimate a measure of association based on a sample. It is possible to draw a bad or unrepresentative sample due to chance alone, meaning the measure of association you observe in your data may be different from the true measure of association by chance alone. Hypothesis testing allows us to calculate the probability that the measure of association you observed in your sample was due to chance and not due to a real effect. Hypothesis testing means that you are performing a statistical test in order to get a p-value. A p-value is the probability that your results are due to chance. A statistical test quantifies the degree to which sampling variability or chance may explain the observed association. So let's walk through an example as we talk about hypothesis testing. Spasmodic dysphonia is an idiopathic, chronic, and disabling voice disorder. In a case-control study, 150 cases of SD were identified along with 150 controls. Of those with SD, 16 had previously experienced meningitis. Of the controls, 3 had previously experienced meningitis. Since this is a case-control study, the appropriate measure of association is the odds ratio. we find that people with SD are 5.85 times more likely to have had meningitis than people without SD. So what is this relationship telling us? Our sample indicates there is an association between SD and meningitis, but now we need to determine if what we are observing in our sample happened by chance. We need to infer something about the population from our sample. So there are two possibilities. Either the association we saw in the sample was a fluke, or there really is an association between SD and meningitis in the population. So how do we determine which is the correct conclusion? It all starts with the statistical hypothesis. We use our research question to develop our statistical hypothesis. We also determine which comparison statistic we will use. Now that we've stated our hypothesis, or now that we've come up with a statistical hypothesis from our research question, where there's two ways that we need to state it. The null hypothesis and the alternative hypothesis. The null hypothesis is always a statement of no difference, while the alternative hypothesis is the statement of difference. The statistical test assesses the null hypothesis. The p-value tells you how likely it is that the observed result that you saw would occur if the null hypothesis was really true. So in our example, for our first step, we must construct our null and alternative hypotheses. The null hypothesis, remember, is always a statement of no difference, while the alternative hypothesis states the difference. So here, our null hypothesis is that there is no association between SD and meningitis. And our alternative hypothesis is that there is an association between SD and meningitis. Next, we set our significance level. Now, the significance level is the acceptable probability of being wrong about the population when the null hypothesis is rejected. We have to set this before we conduct our statistical test. So we want to determine ahead of time what we are comfortable with as far as the probability that we are wrong when we reject the null hypothesis, because the difference we found was simply due to sampling and not a characteristic of the population. Alpha is typically set at 0.05 because we are typically willing to take a 5% chance that we are wrong in our rejection of the null hypothesis. Now remember, alpha is the probability that sampling error alone could have produced the association that we see, and alpha can range from 0 to 100. But why do we care about an alpha of 0.05? Alpha is conveniently set at 0.05, but it can be set higher or lower. What is important is how willing we are to come to the wrong conclusion and incorrectly reject the null hypothesis, which is our statement of no difference, and conclude that there is a real association in the population, when, in fact, there is not a real association. So, in our example, we found an odds ratio of 5.85. Now, I found a p-value of 0.002. We're not covering how to calculate p-values in this course, only how to interpret them, but trust me, this is the correct p-value. We compare our p-value to our alpha. If the p-value is less than our stated alpha, then we conclude that our results are statistically significant, and we reject the null hypothesis in favor of the alternative. Our p-value is 0.002. Since this is less than our stated alpha, we can reject our null hypothesis, the statement of no difference, and conclude that there is a statistically significant association between SD and meningitis. We are saying that we are confident the results are not due to chance alone, and that there really is an association between SD and meningitis in the population. So in our example, we found an odds ratio of 5.85. Now I found a p-value of 0.002. So what does this mean? Remember that we set our alpha value at 0.05. We have to compare our p-value to our alpha. If the p-value is less than our stated alpha, then we can conclude that our results are statistically significant, and we reject the null hypothesis in favor of the alternative. So our p-value is 0.002. Since this is less than our stated alpha, we can reject our null hypothesis, our statement of no difference, and conclude that there is a statistically significant association between SD and meningitis. We are saying that we are confident the results are not due to chance alone, and that there is really an association between SD and meningitis in the population. So p-values give you the probability that chance is responsible for what you observe in your data. P-values are bounded by 0 and 1, and you can never completely exclude chance, no matter how small your p-value is. So you can never mandate chance, no matter how large a p-value is. Finally, p-values reflect both the magnitude of the association and the sample size. It is possible to have a huge sample where even a trivial risk increase or decrease is statistically significant, just as it is possible to have a small sample where even a large risk increase or decrease is not statistically significant. Now, statistical significance is not the same as importance. This is the difference between statistical and clinical significance. Statistical significance refers to the probability of drawing the wrong conclusion about the relationship between variables in the population. Clinical significance refers to whether or not the observed relationship is large enough to care about. Also, there is no such thing as being more or less significant. Your result is either statistically significant or it is not. Now, another approach to quantifying sampling variability is the confidence interval. Now, the actual measure of association given by the dataset is called the point estimate. The point estimate is the value of the association that you observe in your sample. It's your best guess of the size of the association in the population, given the data from your sample. If you were to draw another sample, chances are that you would not find the exact same point estimate for your association, since samples vary. In order to account for the sampling variability, we can calculate a confidence interval around our point estimate. The confidence interval gives us a reasonable range of values for the association. It's the range within which the true magnitude of effect lies with a certain degree of confidence. Note that in our epi studies, the point estimate is typically the risk or the rate ratio, or the odds ratio. Now, a confidence interval can be viewed as a range of possible values for the measure of association that are compatible with the observed data from your sample. When interpreting confidence intervals, we can state that we are 95% confident or 99% confident if we're applying more stringent criteria, that the true value of the measure of association falls within our confidence interval. So that's saying that the true population association, what really is the truth in the population, falls somewhere within that interval. And we are a certain amount of confidence that that is truly the case. Now in our example, we find a 95% confidence interval of 1.67 to 20.56. So we can state that we are 95% confident that the true odds ratio for the population lies between 1.67 and 20.56. God! So in our example, we find a 95% confidence interval of 1.67 to 20.56. So we can state that we are 95% confident that the true odds ratio for the population lies between 1.67 and 20.56. If your confidence interval spans the null value, then the associated p-value is greater than 0.05, and the results are not statistically significant. This is because when the confidence interval spans the null, it means that the null is a possible value for the association. So it's possible that there is no association between the exposure and the outcome. Some other important points to remember are that p-values and confidence intervals tell you nothing about other possible explanations for an observed result. They do not indicate if bias or confounding was a problem. And p-values and confidence intervals do not indicate a biological, clinical, or public health significance of the relationship. So what exactly is confounding? We've been using this word a lot throughout the semester. Confounding occurs when the relationship between two variables is explained by each of their associations with a third variable. So the association between x and y is explained away when you account for z. An example of this is the relationship between alcohol and lung cancer. There's a strong association between alcohol use and lung cancer. However, this relationship disappears when you account for smoking. People who drink also tend to smoke, and people who smoke are at an increased risk of lung cancer. So in this example, cigarette smoking is a confounding factor in the relationship between alcohol and lung cancer. To truly be a confounder, the variable must meet certain criteria. First, the confounder must be associated with the exposure, and it must be an independent risk factor for the disease. So if a characteristic is associated with disease, then the risk of disease is different among people with the characteristic compared to those without. If the characteristic is associated with the exposure, then the distribution of the characteristic is different among people with the exposure compared to people without the exposure. Next, a confounder cannot result from the exposure or be in the causal pathway. An example of being in the causal pathway is that moderate alcohol consumption increases serum HDL levels, which in turn decrease the risk of heart disease. HDL level is a step in this causal chain, not a confounder that needs to be controlled. Rather, it is something interesting that helps us understand the disease mechanism. Let's take a look at confounding bias using the lung cancer and alcohol example. I think the concept becomes much easier to understand when you see it in action. We'll start with the traditional 2x2 table with the disease, lung cancer, and exposure drinking. As we've discussed previously, the relative risk is calculated by finding the cumulative incidence in the exposed, here the incidence of lung cancer in those who are heavy drinkers, and dividing by the incidence rate in the unexposed, the incidence of lung cancer in the non-drinkers. Here we have a cohort study of heavy drinkers and non-drinkers. Our exposure and outcome, heavy drinkers and non-drinkers, which is our exposure, and the outcome of lung cancer. 33 of the 1,700 heavy drinkers developed lung cancer, and 27 of the 2,300 non-drinkers developed lung cancer. Now remember, the cumulative incidence of lung cancer in the exposed group is the number of cancers divided by the number of people in the exposed group, which are the heavy drinkers in this example. The cumulative incidence of lung cancer in the unexposed group is equal to the number of cancers in the unexposed group divided by the total number of people in the unexposed group, the non-drinkers. So here we find that the crude, which is our unadjusted relative risk, is a ratio of the two, and it's 1.65 in this example. So we need to ask ourselves two questions. Are smokers more likely than non-smokers to drink alcoholic beverages? And is cigarette smoking an independent risk factor for lung cancer? For both questions, we must stratify our data based on smoking status. To answer the first question, we need to examine the number of drinkers in each of the smoking strata. In smokers, 80% are likely to drink, so 800 out of 1,000 people. In the non-smokers, only 30% are likely to drink, 900 out of the 3,000 people. We can answer yes, smokers appear more likely to drink than non-smokers. Now to answer the second question, we want to look at the stratum-specific relative risk of lung cancer. That is, we want to examine the relative risk of lung cancer among drinkers for those who smoke and for those who do not smoke. When we calculate the stratum-specific risk of lung cancer for drinkers, we no longer see an effect of drinking on lung cancer. We see a stratum-specific relative risk of 1 for both the smokers and the non-smokers. This seems to indicate that once we take smoking out of the mix, there is not an increased risk of lung cancer due to alcohol consumption. Now, once we have separate tables for smokers and non-smokers, we can calculate the relative risk of lung cancer amongst drinkers for both groups. And as you can see, when we look at each group individually, we no longer see any association between alcohol and lung cancer. So what do we do if we want to know the association between alcohol and lung cancer, but we want to take the effect of smoking out of the equation? We can calculate an adjusted relative risk. In this example, we are calculating the relationship between alcohol and lung cancer, adjusting for smoking status. We can now say that after controlling for smoking, we find no relationship between alcohol and lung cancer. To calculate the adjusted relative risk, for the numerator, you calculate for each stratum cell A multiplied by cells C plus D, and then divided by the total number of people in that stratum. You then sum across all strata. For the denominator, you calculate cells C multiplied by cells A and B, and divided by the total number of people in that stratum, and then you sum across all strata. Let's walk through another example using a case control study that examined the association between oral contraceptive use and risk of heart attack. In this example, we suspect that age is a confounder. First, we calculate our crude odds ratio. We find an odds ratio of 2.2, indicating that people with an MI are 2.2 times more likely to have used oral contraceptives compared to those without an MI. So the first step is to stratify based on the confounder. In this example, age. We create two separate 2x2 tables, one for people under 40 and one for those 40 and older. We can now assess if the potential confounder is associated with the exposure. Here we see that 31% of people aged less than 40 are likely to use oral contraceptives, but only 12% of those ages 40 and older are likely to use oral contraceptives. We have met the first criteria. It appears that the confounder age is associated with the exposure, as indicated by the difference in the distribution of OC use by age. Next, we can look at the stratum-specific odds ratios and see if they differ from the crude odds ratio. Since the stratum-specific estimates are more than 25% different from the crude odds ratio, we do have an indication of confounding. To find the adjusted odds ratio, we begin with the numerator. For each strata, multiply cell A by cell D and divide by the total number of people in that strata. Then add all the strata together. For the denominator, multiply cell B by cell C and divide by the total number of people in that strata. In our example, we get an adjusted odds ratio of 2.79. This is the association between MI and oral contraceptive use controlling for age. Now, why do we want to minimize or control for potential confounders? Confounding factors are nuisance variables. They get in the way of the relationship you want to study. You want to remove their effect. Confounding can be controlled for in both the design and the analysis phases. However, to control for confounding, you must have information on the variables that are potential confounders. To minimize confounding, you can match for potential confounding variables, adjust for the confounding during the analysis, or restrict the study population to a group lacking that particular confounding factor. Now, there may be residual or remaining confounding even after many confounding variables have been controlled. Some sources of residual confounding include confounders for which no data were collected, use of broad categories of confounder in your analysis, and inaccurate data on a particular confounder. Effect modification is present when the exposure-disease relationship varies across a third level or a level of a third of a factor. So how is this different from confounding? Confounding is a distortion of the true exposure-disease relationship by another factor. It's a form of bias that must be controlled for in your analysis. Effect modification is a desired observation. It means that you've identified subgroups for which there is a higher or lower effect. So how do we assess effect modification? Just as we did with confounding, we can use stratified analysis. We actually test for effect modification prior to testing for confounding. If the variable is identified as an effect modifier, then the question of confounding by that variable is moot. We simply present the stratum-specific results and don't worry about computing an adjusted measure of association. Just as with confounding, I think this process becomes clearer if we walk through an example. In this example, let's say we are examining a case control study designed to identify the relationship between exposure to chemical X and the development of cancer. First, remember that the appropriate measure of association for a case control study is the odds ratio. Stratified analysis works similarly regardless of the measure of association that you're using. We begin by calculating the crude odds ratio, that is the odds ratio of the exposure-disease relationship of interest. Once we've calculated the crude odds ratio, then we need to stratify based on our possible effect modifier. In this example, we're stratifying by gender. We find that in men, there is an odds ratio of 60. However, in women, there's an odds ratio of 2. This indicates that there's a much greater risk of cancer due to exposure to chemical X in men than there is in women. Now, we should stop here and report the data as such. Why would we not want to continue on and find the adjusted odds ratio? Because here we have identified two very distinct subgroups with different risk of developing the disease due to the exposure. We would want to know what is different between these two groups. If you find the adjusted odds ratio, you lose all of that meaning. There's a statistical test that allows us to determine if the stratified odds ratios are truly different from each other. However, we're not going to go into the specifics of that test. Generally speaking, if they're about 25% different, you would probably find that they are statistically significantly different using various tests.